Okay, in this segment we're going to continue with our discussion of semiconductor devices or semiconductor physics concepts. And we have a new slide deck, so you might want to grab a copy of that from the Canvas site, the file section, or the week 4 page. I think there's a link to it on the week 4 page. So we talked a little about this idea of electron-hole pair creation, and that type of event where we have somehow we have enough energy absorbed by a valence electron that's participating in gluing the silicon crystal together, liberate it from its covalent bond and make it free to move around and become a conduction electron. And that's possible due to thermal energy, like we said. That's also possible due to other types of energy absorbed by the silicon. For instance, you can have light photons incident onto a chunk of silicon, and visible light actually has enough energy to do this. And so this is actually how photodiodes and phototransistors work. This is how the pixels in your camera on your cell phone actually turn the photons that are coming in a given region into an electrical signal. So what happens is a photon comes in here and liberates one of these electrons in the valence band into the conduction band, and that generates an electron-hole pair, and then the electron might be collected for a certain the number of electrons generated this way might be collected for a certain shutter period of time, and then you read out the number of electrons through some means. And so this sort of generation event can happen thermally, that's called thermal generation, and it can also happen optically, that's called optical generation, and there are other possible ways that can happen. We're not going to be necessarily concerned with quantitative modeling of this type of phenomenon, but it and its complementary process here, if they are modeled quantitatively, typically follow sort of first-order reaction kinetics like you would find in chemistry or so. Recombination is the complementary process where you have maybe an electron, a mobile electron, conduction electron is zipping along, and it meets up with a hole, and that electron fills in the hole, and you have what's called a recombination. And that you have to conserve both momentum and energy in this, and so sometimes what will happen is that in certain types of semiconductors, what will happen is that this electron falling down into this hole results in the emission of a photon. That doesn't happen in silicon, at least it's very, very rare in silicon. It happens actually much more readily in compound semiconductors like gallium arsenide, gallium indium phosphide, that kind of thing, gallium nitride. And you find things like laser diodes and LEDs being made out of those 3,5 compound semiconductors. So while silicon is very good at absorbing light and can be you can easily make like a photodiode or a phototransistor out of silicon and sort of absorb light and get an electrical signal that's proportional to the rate of photon absorption in a given area. It's actually hard to make silicon emit light efficiently. That has to do with something called the direct band gap structure versus an indirect band gap structure. 3,5 semiconductors have a direct band gap structure where this kind of emission of an optical photon is very likely. Silicon has an indirect band gap structure, which makes that much more unlikely. And so what happens to conserve energy in that case is that you have a lattice vibration, or sometimes called a phonon, which is sort of a sound wave particle thing, propagate from this event in silicon. So we're not necessarily going to be, like I said, quantitatively modeling these processes, but it's important to understand how certain effects come about, to understand that they exist. And so there they are. So now we want to consider what happens when we have a chunk of p-type silicon and a chunk of n-type silicon, and we're going to slap these together and consider what happens at the interface between them. So in this picture, this yellow region here is meant to be doped p-type, and it's fairly lightly doped. And so we talk about, or we denote, the qualitative level of doping of a region by a superscript. So if you have something like P minus, that would be a lightly doped p-type region. And lightly doped in terms of actual volumetric concentrations might be kind of in the range of like 10 to the 12th per cubic centimeter to maybe 10 to the 14th per cubic centimeter, maybe 10 to the 15th per cubic centimeter. And if I don't have a subscript, or a superscript here rather, and it's just P, or like over here this n-type region just has an n with no superscript, that's a moderately doped region. And that moderate doping level might go from like 10 to the 15th up to maybe like 10 to the 17th or 10 to the 18th per cubic centimeter. And then if we have a really heavily doped area, we denote that with a superscript plus, so it would be like a P plus or an N plus region. And that might be kind of in the range of 10 to the 19th per cubic centimeter to 10 to the 21st per cubic centimeter, maybe 10 to the 18th, 10 to the 20th per cubic centimeter, something in that range. And when you're getting into that sort of heavily doped area, you're not quite to the level of a metal, but you're pretty close. That's a pretty conductive chunk of silicon. And then we sometimes will dope even at a slightly higher level, and that would be called degenerately doped. And that is practically behaving like a metal for all intents and purposes. And so here we have a relatively lightly doped p-type region and a moderately doped n-type region. So I've tried to represent that, although it's impossible to do so quantitatively, I've tried to represent that with sort of the density of these black ovals and these white ovals here. So the white ovals with the minus signs and the white ovals with the plus signs are meant to denote ionized acceptors or ionized donors. So these are the space charges. These are the, in the case of the acceptors, these are the lattice that have been replaced by, where a silicon atom has been replaced by a group 3 element, and you have that one extra valence electron filling in the hole that the acceptor came with, and that creates a fixed negative charge in space. Over here, these white ellipses with the plus signs are meant to represent those ionized donors, or these group 5 atoms that have had that extra 5th valence electron ripped away, and that leaves an uncovered proton in the nucleus that's in this one fixed lattice site. And of course, the conduction electrons and the holes are still around, and on average, these regions are charge neutral. Okay, and that's what these black ovals and these black ovals over here with the plus and minus signs are meant to represent. So these dark circles with the plus signs are representing the mobile holes, and these dark circles with the minus signs are meant to represent the conduction electrons. So over here we have lots of conduction electrons, relatively few holes. Over here we have lots of holes and relatively few conduction electrons. And what we're going to do is imagine sort of slapping these things together. Well, what's going to happen? Well, over here we've got lots of holes and relatively few electrons, and over here we have relatively few holes and lots of electrons. And so there's going to be a tendency of the holes to want to diffuse over to the N side. And there's going to be a tendency of the electrons in the N side to diffuse toward the P side. And what happens when those electrons and holes get together in this area near the interface is that they basically annihilate each other. You have recombination taking place, and you have basically a region here which is devoid of mobile carriers. Okay, so the electrons in the holes go away, and that leaves uncovered the ionized donors on this side and the ionized acceptors on this side. So these are fixed space charges that have a positive charge, and these are fixed charges that have a negative charge. And when you have a separation of charges like that, that creates an electric field. And the field lines start on the positive charges and terminate on the negative charges. And so for every positive charge over here, that sends out a field line, and that has to terminate on a negative charge. And so for every positive charge on the N side of the junction here, we have a corresponding negative charge on the P side of the junction. So this region is called a couple of different things. This region is called a depletion region because it's a region that's depleted of mobile carriers. It's also called a space charge layer, and that's because these space charges, it's a layer that has basically space charges exposed. So I'll usually be calling it a depletion region, but you sometimes will call it, you'll see it called a space charge layer, or SCL. And so this electric field that's set up actually tends to oppose the motion of the carriers due to diffusion, right? So here, the electrons are attracted to, like any electron in this region will be attracted to the positive charges. They'll be pulled to the positive charges and repelled by the negative charges, and they'll want to go this way. And that has a tendency to oppose the motion of the electrons over here due to diffusion down there to their concentration gradient. Likewise, any holes in this region would want to be attracted to the negative charges and away from the positive charges, and they're going to go toward the P side. And that's going to cause a drift current, or a tendency of these carriers to drift back to oppose that tendency that they have to diffuse. And so this electric field that's set up by depleting this region of mobile carriers actually opposes that diffusion until you get an equilibrium set up. And this is kind of the same equilibrium that we talked about last time in the last segment with the Boltzmann distribution. And so what we'd like to do is to think about what might the energy landscape look like for an electron as we go across this p-n junction from the P side to the N side. Okay? And in order to do this, we need to use some of those electrostatic relationships that we talked about. So if you recall, basically the electric field through Gauss's law is related to the integral of the unbalanced charge density. And so we're going to basically try to make a plot of the unbalanced charge density. So I'm going to flip over to a whiteboard and try to sketch this. So we had here a picture that looked like this, where this was our P minus and our N region, and we had a depletion region edge here and a depletion region edge here. And we had a bunch of space charges with minus signs here, and we had a bunch of positive charges here, and we had our field lines. But we want to think about, what does this charge density rho look like as a function of position as we go along here. So I'm going to take x equals 0 to be the junction edge. And as we're in the bulk of the P region over here, okay, this is all charge neutral. We basically had just as many mobile holes per unit volume as we did ionized acceptors. And so the actual unbalanced charge density over here is 0. And so the charge density in this region is just 0, up until we get to this dashed line, which is the edge of the depletion region. Well, then we see a bunch of negative charge that's unbalanced. And if we assume, our typical assumption is that there is a fixed concentration, or constant concentration of acceptors. So there's a concentration of acceptors in this region, which is called N sub A, for the concentration of acceptors. And there's a concentration of donors in the N side, which is typically called capital N sub D. So this is the concentration of acceptors. This is the concentration of donors. And so what we get is basically a constant charge density of minus q times n sub a. So this is minus q, the charge on an electron, times n sub a. So it goes from 0 and it steps up to this constant minus q n sub a. And then when we get across to the n side of the junction, we're going to have a different level that's constant, which is positive q n sub d. And then up to that dashed line, and then we're going to go back to the bulk of the n region where we're back at 0. So that's charge neutral. And so we sort of have this type of situation here. And note that because we said that there's a corresponding positive charge, there's a corresponding negative charge to every positive charge over here, that means that the area under these curves has to be the same. Okay? But to get the electric field profile, actually maybe I'll draw this up here a little bit. What we have to do is we have to integrate. So E is proportional to the integral of rho dx. And so to get the electric field, we just have to integrate this curve. And so as we're over here, we're integrating 0, and we get 0. And then we hit this step down, and so we're going to be integrating some constant, and the integral of a constant is just a line with a fixed slope, and the slope is negative until we get here to x equals 0. And then we're going to be integrating a constant positive quantity, and so that's going to give us a line with a positive slope. And notice, because these areas are the same, we have to get back to the same level here. And so we get a little triangular profile where the electric field increases linearly up to some maximum value, and then it decreases back down linearly on a different slope to 0 as well. And the maximum electric field is going to be right here at the p-n junction boundary. And so to get the electrostatic potential, what we do is we integrate this electric field profile yet again. So psi is proportional to this integral of E dx. And so psi will give us something like this. So we're integrating 0, and we get 0 up to this point. And then we're integrating a line, or a ramp. We integrate a ramp, we get a parabola, and the concavity of this parabola is going to be down. So it's going to look something like that. And then we're going to be integrating a different ramp with a slope that's positive, and so we're going to get a parabola that has the opposite concavity. Since the slope is the same here, it's going to be continuous and differentiable through this region, but they're going to be different parabolas with different concavities. And then we're going to get back to integrating 0 again. And so here we're down at a different level. And this total change in potential is called the built-in potential, and it's sometimes denoted psi 0, built-in potential. And this is actually a physical way that we can get this sort of energy barrier that we talked about in the last segment that arises in connection with the Boltzmann distribution. And so basically we're going to flip back to the slides now. And this is the kind of situation we have. So here the distance, the thickness of this depletion region, here we're calling D. That's the width of this sort of piecewise parabolic region. And here is size 0, the built-in potential. And now what we're going to do is consider sort of equilibrium conditions in our PN junction. Here we've suppressed all the ionized donors and acceptors in the mobile carriers. So there's still a lot of mobile carriers over here. There's still a lot of mobile carriers over here. There's still those ionized donors and ionized acceptors, but we're just suppressing them. And we're just showing the space charges here in the depletion region with the field lines up here in this picture. And here we've taken that sort of energy profile, we've converted it into this so-called energy band diagram. So here is the conduction band edge. This is the lower edge of a band of energies in which the mobile carriers, the mobile electrons, the conduction electrons can live. And here is the valence band of energies, which is the range of energies that electrons that are in covalent bonds in the crystal, gluing it together, can live. And it's also the energy levels where the holes live. So over here we have lots of electrons in this n-type region. The concentration is basically n sub d. Concentration of holes over here is relatively high, not as high as the concentration of electrons. Concentration of holes over here is basically n sub a. And so what will happen is there's going to be an equilibrium between drift and diffusion, and there will be the ratio of the concentration of electrons to the concentration of holes here is going to be e to the minus barrier height, psi 0 over ut, and the same is true for the ratio of the concentration of holes here to the ratio of concentration of holes here. And you've got a tendency of these holes to bubble up and of these holes to try to diffuse down their concentration gradient. You've got a tendency of these electrons to want to roll downhill and a tendency of these electrons to want to diffuse down their concentration gradient, and these two things are in equilibrium. They're balanced. And so if we were to, let's say, apply a positive voltage, so we slap a contact onto this side and we slap a contact onto this side, and let's say we put ground on this side and we put a positive voltage here, what's going to happen is that we're going to be reducing that built-in potential by the amount of the applied voltage. And what that means is that there's going to be a reduction in the depletion region width and this electric field, and that's going to reduce the tendency of the electrons to roll downhill here, to drift, and of these holes to bubble up, and it's going to exponentially increase the number of carriers here that have enough energy to go this way. And so the diffusion current is going to be greatly accentuated, and the diffusion current here is going to be accentuated. Now, of course, because there are so many more electrons here, most of this diffusion current is going to be electron flow here, but there's also a small amount that's also hole diffusion current in the opposite direction. So we're going to get an accentuation of diffusion and a suppression of the drift current component. And this condition where we apply a positive voltage to the P side relative to the N side is called forward bias. And that's going to have a tendency, as we'll see, to greatly increase the current from the positive side to the negative side here. So remember, conventional current is opposite the direction of the flow of electrons. It's in the same direction as the flow of holes or positive charges. So that's what conventional current is. So reverse biased is either zero bias or a negative bias. Okay, so here with the built-in potential and no voltage, external voltage applied, there should be basically zero current flow in this situation. If we instead apply a positive voltage to the N side relative to the P side, now this is a more substantially reversed bias condition, and in this case that voltage accentuates or adds to the barrier height here. And so the barrier height goes from psi 0 to V plus psi 0. That's going to thicken the depletion region some, and it's going to increase the electric field. Okay, so there's going to be more electric field, so stronger electric field, which means that any carriers that are here are going to get swept to their respective sides, and there's going to be exponentially fewer carriers that have enough energy to get over the barrier. So we're going to be accentuating we're going to be accentuating drift and reducing diffusion in this kind of situation. Now, there can be a small amount of current flow, and that current comes from the fact that if we have a thermal generation event, so let's suppose we have one of those thermal generation events here in the depletion region, where we have a new electron-hole pair created. Well, if that happens, the electric field is such that this hole is going to get swept over to the P side, and this electron is going to get swept over to the N side, and those will come out and be collected as current. So there's some rate of generation of these carriers, and that rate of generation and the collection of those charges becomes a small amount of reverse junction leakage. And so this might be on the order of something like 100 femtoamps, which is like 0.1, it's like 100 times 10 to the minus 15, so it's like 0.1 picoamps, 10 to the minus 13 amps. It's not a very large current for a typical size junction, but it's not zero. And so this is the origin of that so-called reverse junction leakage. That's the IS parameter in the ideal diode equation, basically, is this reverse leakage current that comes into the ideal diode equation. That's the -1 term. So you get IS times -1 is the current in the reverse bias direction. And this is also how photodiodes work. We tend to run them either at zero bias or reverse bias, and any light that shines on this depletion region will basically generate electron hole pairs due to photogeneration, and the field will sweep those electrons and holes apart, and we'll get a photocurrent that's proportional to the flux of incoming photons. So anyway, that's it for this segment, and next time we'll take a look at least in a hand-wavy way, where this ideal diode equation comes from. Okay, so we'll see you next time.